all doing well. My name's Sean Carey. Yeah, I had some Zoom issues and I wasn't helped by my cat this morning. So what I'd like to talk about today is the legacy of the Spitzer Space Telescope in you. So I'm going to give a very brief overview of Spitzer. I'm going to talk a little bit about how you can find the data, which can help you do the best science possible. And then I'll talk about some things that we're doing at the Spitzer Science Center as we ramp down to make the data of even higher quality for your future endeavors. Okay. All right, so for folks who may not be familiar with the Spitzer Space Telescope, it is the last, the fourth of the Great Observatories program run by NASA, which included HST and Chandra. It's a small telescope, 85 centimeters. It's in an Earth trailing orbit. It's very cold, always at cryogenic temperatures. So it has very low background in the infrared, which is where it took its observations. It had 3 instruments, a set of 4 cameras from 3 to 9 microns called IRAC, a set of spectrographs from 5 to 38 microns, which were reasonably low resolution, but very useful, called IRS. And then a set of imaging cameras and a broadband spectral energy distribution instrument at 24, 70, and 160 microns called MIPS. It launched in 2003. It had a 5.5-year cryogenic lifetime. It outlived all expectations as far as the cryogen. And part of that was because it's passively cooled. It had a shiny side facing the sun and a side that was painted this burr black to radiate in the cold space. And that worked really well. In fact, it worked so well that even after we ran out of the cryogen, which is the death for most infrared missions, Spitzer could still continue, not with a full-blown suite of instruments, but only with the 2 shortest wavelength cameras, the 3.6 and 4.5 microns. And we did that for another 10.5 years, and it was really successful. In fact, folks were very imaginative and used the data about as best as I think anybody could. And ends up 3.6 and 4.5 microns, or almost L and M band, are really useful pass bands to be able to go down to the background limit. Unfortunately, operations ended this year, early this year, at 30 January 2020, and spacecraft was decommissioned. There's over 9,000 publications and counting. So I'm hoping that some of this information that I'm going to give today will help you add to those publications and you get good science done. What I'm showing here is just an example cryogenic Spitzer image using the IRAC cameras from 3 to 8 microns and the MIPS 24 of HH 36 through 38. You can see the nice bipolar outflow there. And then overlaid on top of that now is what the IRS spectra looks like of this, the central embedded protostar. And you can see the silicate feature and water ice and a lot of good, interesting things. So the data set is very rich. It's publicly available. It's all there for you to use to exploit. Okay. So some of the things that I'll brag a little bit about Spitzer, some of the transformative science it did is it revolutionized our understanding of exoplanets. It made the first temperature map of an exoplanet. So I'm just showing a graphic of HD 1897733b, in a longitude representation of the temperature of this tidally locked hot Jupiter. It also showed us a lot about our own solar system, but also other solar systems. So one of the things that was nice is the IRS spectra of comet Hale-Bopp compared to a extra Zodi disk of HD 69830, I'm sorry. And you see they have very similar composition. That's telling us something about comparative planetology and diskology between our own solar system and other solar systems. So I'm just going to breeze through these. I mean, there's a lot of Spitzer results in 9,000 publications, and I cherry picked the things that I thought was interesting. One of the things I'm very interested in is our own Milky Way galaxy and star formation. And Spitzer spent a lot of time looking at our own Milky Way, and was able to peer through most of the gas and high dust and high extinction regions in our own galactic plane to look at not only the star forming content, but also the stars themselves to help us actually map out what the Milky Way looks like. So here's a representative cartoon, which doesn't quite, it's more illustrative because we didn't get quite to the far side, but if you use symmetry arguments, this is what we think our best picture of what our own Milky Way looks like. And then using those same instruments, we can look at the very high redshift universe to map star formation. So now what we have is a map, a plot of the star formation history of the universe on the right-hand side. And while UV and optical measurements contribute to low redshifts from 0 to 2, at higher redshifts, you really only can measure the star forming content in the infrared. And Spitzer is able to allow us to measure the star forming content to 8 redshifts of 8 or more than 12 billion years in look back time. All right, so hopefully that'll whet your appetite for interesting things you can do with Spitzer. So let's talk about how you can get to the data. So all the data is available through Ursa. There's processed images that come right out of the pipeline and they're for use, calibrated spectra and mosaics. On the right-hand side, it shows the coverage of all the Spitzer observations taken. And you can see that line, it's an ecliptic coordinates, and that V-shaped line is, of course, the galactic plane. But there's Spitzer observations everywhere. Almost everything interesting after almost 20 years, we tried to observe. Through the archive, you can do positional searches and target searches. You can also look at solar system objects. So here's an example of the primary search interface. It's very simple. Most people will do either positional searches or they'll go down and look at a moving object and type in the NAIF ID or the object name. It also resolves targets using NED and SIMBAD. You can go to the URLs below to access the interface. That's the first one. So for the Spitzer Heritage Archive. The other thing interesting that you can do with all the Ursa services, or most of them anyways, is do pre-covery of solar system objects. So if a Spitzer observation wasn't of a particular solar system object, but that solar system object happened to wander through the background or foreground in most cases, while people were taking their observations, you can actually go and see which observations would have your favorite solar system target, and you might get more information than you thought was previously possible. In addition, there's a set of visualization tools built right into the archive, so you can go and browse through the data and see what you like, what you don't like, just showing an example of a star-forming region in the galactic plane. And there's a really excellent set of tutorials on the Ursa IPAC YouTube channel, which is you can get through the Ursa website, and the URL is listed at the bottom there. So I encourage you, if you want to learn how to exploit the archive and do things that I don't even know how to do, go watch a couple of YouTube videos and learn. Okay. One key component of Spitzer was not only was it for a general observing observatory open to the entire community, but the community was also encouraged to come up with a set of large coherent observing programs, legacy class programs, and this was built into Spitzer from the beginning. And so those legacy program observers really delivered, because we required them not only to come up with really great observations that used a fair amount of observing time, but also to deliver enhanced products. So high quality mosaics, source catalogs, process spectra, ancillary data. And so there are 9 galactic and 27 extragalactic legacy data sets available on the Ursa website as well at the URL at the bottom of the page. And the graphic's just an example of one of the biggest and most used, which is the glimpse survey of our own galactic plane. It spans the whole 360 degrees of the mid-plane, going about plus or minus 2 degrees in most places. And it's really fantastic. More than half of the 9,000 publications to date use legacy data. And there's still a lot more in there. Hasn't been mined at all. So you really should go and look at your favorite sources using legacy products and see what you can discover. One of the other things that's really important is some of the programs worked in time series. So, and this is one of the things I think going forward that you're going to find with Spitzer, because it has such a long temporal baseline now. And we have looked at some sources over and over again, like star-forming regions like NGC 2264, which the graphic is a snapshot of the time series of objects in there. And there's a little blow up so you can see one that's fairly periodic. So it's telling us a lot about disk physics accretion in this particular object data set. But there are also plenty of other serendipitous time series observations. Like we observe the galactic plane not hundreds of times, but multiple times. So you can get multi-epoch things. So you can look for proper motions. You can look for variability. You can, people have actually started to use this to look for collisions in planetary systems where extrasolar asteroids have collided and produced a burst of dust, and you can capture that because it's the 4.5 micron emission Spitzer spikes and then tails away. And if you have enough coverage, you can actually see that. So I encourage people to think about the time series applications of Spitzer as well. Okay. In addition to the legacy products, one of the things we did to make sort of an extra legacy product from the Spitzer Science Center is we took all the Spitzer data, as there were many observations where, first PI observed a star-forming region, second PI observed a star-forming region that's pretty close, and they sort of overlap. And what we've done is we've taken all the data for a region of sky that are contiguous and mosaic them together and created source lists. And these are the Spitzer enhanced imaging products. And the URL for accessing it is on the slide below. And the graphic there just shows you what the main interface looks like. So it shows all the Spitzer observations that have been mosaic to produce the enhanced imaging products. What we did not do is that there was a legacy science team product that did it better. We didn't mosaic those as well. So the galactic plane has more coverage from the glimpse and follow-on surveys than you'll see in the enhanced imaging products. And basically all you can do, it's a simple interface. You type in your target or your coordinate and you go look and see what we have there. So not only are there mosaics co-added with as much data so they can get very deep, particularly at the north ecliptic pole, where we did a set of SkyDAR calibrations for Spitzer, and we did that every 2 weeks, and they're incredibly deep by now. So that's an interesting data set. And also a set of source lists where aperture photometry, signal noise greater than 10. They're reasonably reliable. We're not vetting and guaranteeing that every source in the list is a bona fide real source, but you should check if you see something interesting or really interesting in the data. Just confirm it before you publish it. The cryogenic products are available now. So that was the first 5.5 years of data. We're working on the post-cryogenic products, and those should be ready in summer 2021, which is not too far away. And that's a lot more data, 3.6 and 4.5 microns. We have another 10 plus years of data for you to exploit. Here's just an example, 4.5 micron super mosaic of M101. There are multiple observers who are interested in different aspects. And so this is what it looks like. You can see it was taken at many different roll angles. So there is some temporal information there in the individual data, but in the mosaic that all gets squashed down. So you have as deep an image as possible. Okay, so that's a very high level overview of how to go get the data and exploit it. And I just want to spend a little bit of time talking about the things we're doing now, because this meeting and doing this webinar is a little bittersweet for me, because I've been representing Spitzer at the AAS for since 2003 now. And this is the last winter meeting where we're going to be having something from the Spitzer Science Center, because in summer in just a few months, we're going to be closing up shop, and all the data and all the documentation has already been transferred to URSA. We're still providing expert support, and I'm going to give you a couple of things that we're working on wrapping up, which we hope are value added to the community. And most of the folks are staying around. Thanks, Debbie. Most of the folks are staying around, so we'll be able to still provide expert user support through URSA, and we're not going to get rid of any of the old URLs. So if you're typing what you remember, it should still work, and if not, you can where we are, so you can find us. One of the things we're doing now, this is a work led by Jessica Crick, is a uniform reduction of all the post-cryogenic exoplanet and brown dwarf time series, which is a lot of data. This was a major effort because exoplanets got really interesting, and Spitzer could do a lot with transiting exoplanets. Is we could, after careful data reduction, get down to precision floors of 30 parts per million, in the best cases. But the state is also challenging. You have to have some ninja level data reduction because of the instrumental systematics. And what Jessica and her team have done is they've done a uniform reduction using machine learning techniques, particularly random forest. And what I'm showing on the right-hand side here is the comparison of the uniform reduction, which is the black points, which is the blue and the red points, to the black points, which are a set of community best reductions of this. So you can see there's some scatter in the community best, and the random forest uniform reduction has more scatter, but it's pretty close. The interesting thing about doing this uniform reduction is that most reductions of exoplanet staring mode data use the science data itself to do remove the systematics. You model the systematics in the data set that you're trying to extract the science from. And that can do some aliasing if you're not really careful, but folks have been very careful. This uniform reduction actually uses an independent data set, a calibration data set, which we took calibration stars in the same staring mode observation method as people did for their science, and models the systematics using that calibration data, which is an interesting new technique for it. And I think that the data set is useful for you as a browse quality reduction, as a quick look, so you can go look, see what's going on. If you can't find the paper, maybe that data wasn't produced by any science team. And you can also use it to compare to your own results. So you should, hopefully, if you're working really hard on a data set, you should do better than the uniform reduction. But also provides us a tool, I think, which in the future, as we understand a little bit better more about systematics in general and how to do these uniform reductions using calibration data sets, I think this could be a very powerful tool for future exoplanet photometry and spectroscopy with JWST and aerial. And I encourage everyone to go look at Jessica's paper about this because there's a lot more information. Okay, so one of the other things we're doing is we're improving the astrometry. We got all done with the processing for the cryogenic data, and then, you know, Gaia, it keeps coming out with wonderful astrometry. So we're going to reprocess all the post-cryogenic data, all 10.5 years of it, with Gaia DR2 as an astrometric reference. So it gives us improved astrometry from the 2-mass UCAC4 that we used before, mainly improved proper motions for some of the sources that are used to give you an astrometric reference. And it includes a 5th order distortion map, which is good to 30 milliarc seconds. So the top is the Gaia proper motions as reduction using the Gaia astrometry, and the bottom is the same reduction using UCAC4. And you can see the Gaia makes it better. It's still not quite perfect. And that's because we're still limited by the fundamental uncertainty in the IRAC centroiding. But it'll be better. It's the right thing to do, and we're doing it. Okay, so sorry I arrived a little bit late, had that Zoom confusion. If you have questions, I'd like to, you know, I'll answer as many as I can now, or you can contact us at help@spitzer.caltech.edu or URSA support at ipac.caltech.edu. Thank you for your time.
All right, if anyone does have any questions, you're more than welcome to unmute yourself and ask those questions, or you can put them in the chat box, whatever you're more comfortable with. We just have about 5 minutes left until the meeting will end. All right, so we have many folks leaving, so last call for any questions. Okay, we got one in the chat box. Either you can read it, Sean, or I can read it, whatever you want me to do.
Okay, so Bill Waller asks, do we have time series observations of older globular clusters? I don't know the answer to that. It's possible. I think, Bill, I'd say, you know, type in your favorite cluster in the search tool and see what comes up. I really don't know. I do know we had a couple of dedicated programs for AGN variability. Yeah, I'm sorry, I don't have a better answer than that.
I do also want to say that if you guys want to ask any questions after this, you can visit their exhibit booth, or you can visit their Slack channel. Yep, but other than that, if we don't have any more questions, we'll go ahead and end here. Thank you, Sean.
Thank you. Thank you, everyone. And thank you for your support of Spitzer. It's been a pleasure serving the community as part of the Science Center. We really enjoyed helping everyone out with observations from the telescope.
Right. Have a good day, you guys.